Okay, my name is Jerry Thomas. I'm from the Milwaukee School of Engineering, and my talk is my experiences on teaching computational engineering to a variety of students. About a year ago, I had a conversation with Stephen about the possibility of teaching a course on computational engineering at MSOE, and I was faced several challenges to do that. First of all, MSOE did not have a mathematical license, so that was one of the first problems. And I wasn't sure how to work it into the curriculum. That was another problem. Wasn't sure what kind of book to use, which was a third problem. So in rapid fire succession, I ended up solving all these problems. And I ended up using Stephen's book. I should say that one of the things I do as an adjunct is I end up teaching a variety of courses, some in software engineering, some in computer engineering, some in electrical engineering. And the advantage of that was when we talked about having the course in our department, it sounded like it would be a course that would appeal to all three different disciplines. And the best choice seemed to be to target it for people who were seniors and would use this course as one of their required electives. And so that's what we ended up doing. So I'm going to go through and tell you a little bit about some of my experiences in teaching the course. My personal motivation for doing the course is that some of you know for a long time I've been working on advanced decision theory based on game theory. And I was hoping I would teach a course on that in MSOE, and I thought this might be a reasonable start for that. And I also thought that I might teach some other courses, all of which would be based upon Mathematica. So I'll go through and tell you a little bit about that. So I'll talk about what I thought about computational engineering, a little bit about how different people in these different disciplines visualize data, because it's really quite different, and some of the simulations that seem to be effective. And also, I would love to talk about the stuff on game theory. All I can say is, I just finished the book. It's at the bookstore downstairs. So here's my plug. So now I don't have to talk about that, right? So for my cursor again here. So what about the computational engineering course? So I had some opening questions. It may be hard to see. Yeah, that means I have to use my glasses because I can't see close up. How about 200, right? Oops, I can go to 200, right? How about 200? Okay, your eyes get old, right? You can't see close. Never mind. I was asked to talk, lead a discussion at Carthage this last summer about teaching a course like that. And I thought some questions were kind of interesting, which I would share as kind of an opening to the course that I did teach. Because I had different disciplines, what is it that the disciplines have in common? How do you teach to different disciplines? And of course, in today's age, because I also teach freshmen, and I find that the freshmen that come from a variety of backgrounds. I mean, even though you think that they all have the same SATs or whatever, they're not really the same. What do the disciplines have in common in terms of their language? Do they use a common mathematics or a common way of visualizing? Do they do simulations? And can just a group like this sort of pick up Mathematica? I mean, I wasn't sure whether that was going to be possible. So I needed to have a definition of what I thought computer engineering was. It may not exactly coincide with what Stephen thinks, but I think it's similar. I see it as a method of how do you analyze data sets, whether they're large data sets or small data sets. So it's a way of thinking about data, so that's one of the things. It's also a way of simulating. If you see if you see data, you actually don't know what it means. So you have to have a model, some way, some conceptual way of thinking about it, and you use the conceptual way of thinking about it by creating some kind of simulation. So one of the things, the strength of a computational engineering approach is, how do I look at the data, large and small sets? How do I simulate large and small sets? And then how do I bring the two together and make a comparison to see whether I made any progress? This is the, let me go down here a little bit. These are the course outcomes. You know, in a university setting, you have to say, at the end of this course, what are people supposed to get out of it, right? So I wanted them to be, first of all, competent in programming. I should say that I had tried an approach before. I had used, without a license, tried to teach people Mathematica at MSOE, and I found that if I started at a fairly high level, the electrical engineers would stop paying attention. And the software engineers who knew Java said, we already know programming, that's just another programming language. And they stopped paying attention. And the computer engineers said, we don't even want to hear about it. So I knew what my challenges were. So, and I couldn't get them to be competent. So one of my goals, this first goal was non-trivial. And I really wanted them to walk away saying, we know how to use this for the rest of our life. This is it. They should be able to create short program segments or language segments. They should have some knowledge of some of the more arcane parts of Mathematica, just to see if they could really pick it up. And the key thing for simulations is solvers. So you need to be familiar with all the different kinds of solvers that are there in Mathematica. And the key thing for visualizing are sort of plotters. So if you can get them to know how do you make plots, how do you do simulation, how do you do solvers, you're kind of there. Okay. So I'm going to fast forward, just in case I run out of time. I want to give you the end story. I should say that the people that I started with from these three different disciplines had no knowledge of Mathematica. The electrical engineers had no knowledge of programming. The software engineers had no knowledge of simulations. All they knew were graphs. And the computer engineers knew C and MATLAB. At the end, I asked them to each do a project in their respective domain, using Mathematica, using all the things that we had learned. This was one of the projects. And the person gave me a full notebook explaining what an L system was, showing me simplified examples of weeds, building it up from weeds to weeds that had colors and colors that had branches, branches that had leaves at the end that were still brown, and then branches at the end like this, which was a real tree. And then what would happen if you varied some of the algorithmic parameters? So I was really impressed. And some of the other projects at the end were, some people were interning in industry. They applied the project to one of their industry type problems. Some people were working on senior design. They applied it to their senior design problem. The SCs, as you might imagine, applied it to Pokemon. But the point is, they all did their thing, and all were very happy at the end. So my approach was very different, having learned that approaching it at the level that I thought they were at was going to be a total failure. I said, why, the thing about using Wolfram's book is it's written for people who are like high school, junior high school students, right? And I'm not ashamed. That's the way I learn. I learn and I go find some very simple book. I read The Little Prince, I learn about literature. So I said, let's use this book. It's got so many sections or chapters, like 1 through 50 or say, whatever it is. And let's just march through. And every week we'll do some number of chapters. You can read it anytime you want. You can keep up. It's so simple. You would be embarrassed not to show up at class that you don't know this stuff. And so one of the first things it did is it taught people about lists and list plotting and colors, and they could start doing simple things with it. About midway, I should say, MSOE is on a quarter system. So 3 weeks into it, 4 weeks into it, we have a midterm. Or 5 weeks into it, we have a midterm. So about midterm, this is the kind of problem I was already giving them. I talked to them about learning sets, training sets. So I asked them, I says, here's something in the Wolfram help. I just extract it, right? But then I said, first of all, I want you to do your own training set with pictures and identify people. And then I gave them a problem, and I said, a couple of them came up with it by themselves. How about if I give you even numbers and odd numbers, can you create a training set that works? And as far as I know, you can't. I asked Stephen, actually, just this afternoon. He doesn't know how to do that one either. But why? Okay, the why is it's a really bad set, and except the answer is obvious. 2 is even, 4 is even, 5 is odd, right? Because it's algorithmic. You know exactly what the answer is. That's a good context setter for this, okay? Doing pictures works in the Wolfram help thing because all the real work has already been done. You give this to students, and the first thing they do is they try to do training on those 3 pictures. So what goes wrong? They're different sizes. They have different color spaces. Where's the head? Okay, is it over next to the guy's bow tie? Or is that part of a face? Or are there people around that have bow ties as part of their face? The reason the training sets work is you have to go through a process, and for time I won't actually try to run it, but the process is you need to get the pictures to have a size. You need to get rid of the color space so that you're down to like a grayscale or something. And once you've done that, all of a sudden the training set works. And you know that probably. The students didn't know that. So when they were doing the homework exercises, they got it all wrong. And so then we would have this discussion. How come this doesn't work? Okay, and then I would give them the explanation I just did. And notice, in doing this exercises, look at all of the technology from Wolfram stuff they had to understand. They're already doing rules with the triple ats and the transpose ats, and they're having to think through all of this. This is after 5 weeks. And I was very impressed. And that meant that my software engineers, my computer engineers, they're all on board. Now, the different disciplines focused on different things. Like this was a picture that the software engineers could really hone in on. Computer engineers, electrical engineers were sort of there, but had a hard time keeping up. Another thing for the software engineers is once you can, all right, aborted, that's okay. Give them a list. This is American Airlines financial data. Okay, so it's now easy for them to pull that off of the web and get a time series plot. They know how to do plots. But you can ask some interesting questions which go way beyond the simplicity of this example. For instance, this is a jaggedy plot. Are these things correlated in a causal manner? That's kind of an interesting question, right? Because normally we think it's just statistical things. If I were to make a plot of the time series against the time series, the correlation between adjacent points, it should just be white noise, right? So, real simple, thought-provoking question. to them is, what do you expect? White noise. This is what you see. It's not white noise, is it? It has structure. It indicates that there are some causal effects. And if you thought about it, well, stock markets actually do care about what happened yesterday and what other stocks are doing. There are some cause and effects things. Now, how do I get the electrical engineers, computer engineers on board? Because software engineers, they like the beautiful pictures and the visualization. Electrical engineers, they are heavily into simulations. So this is the world they live in. The world they live in had been dictated by 4 years, or 3.5 years, of using multi-sim and tools. And they don't even think anymore, they just use the tools. So if you say, what's the behavior of an electrical circuit, then they go, well, I go to multi-sim and I draw these pieces in there and I push start. And if they get an answer, they don't actually know whether the answer is right or wrong, they just know, but I press start and I got this stuff. So since I've taught those courses, I know what their problem is. When I give them homework assignments and say, okay, calculate for me by hand on a midterm, what are the voltages at each point, they get it all wrong. So they don't have a simple way to do the algebra. It's the problem of algebra and getting the unit straight. I will ask them, okay, gee, I got a 1 farad capacitor and it's right here. And they go, okay. Really? 1 farad. So I say, okay, if I have a plate, 1 millimeter apart from another plate, how big is the plate? Anybody know? Some miles or something. Big. Then I said, I just read in a spec sheet that they're selling, these cars that drive along with big boom boxes. They have 1 farad capacitors. Is that true? Yes, it is true. But that's what thinking is all about, right? Then you say, okay, so why is it true? Well, you still have the problem of the spacing, but you could make it really complicated and fill the volume in a different way, and you could put a dielectric in there that really improves the capacitance, and you can do it. And someday, 10 years from now, 50 years from now, we'll use 10 farad capacitors as batteries. So they're just storage tanks. So here's the way they normally solve problems. Set up a problem in steady state, it's algebra. Have somebody do the arithmetic, the units for them so that 1 farad is going to get interpreted correctly. Do all of that. Do a solver, right? So you just have to solve, physics and electrical engineering are very simple. You have a couple of laws, conservation of energy, conservation of charge. You put it into some vernacular, and it will give you the solution. And boy, Mathematica does that pretty nicely. And for my electrical engineering students, they want to do problems like this. Different problem. Same picture, same multisim. Different button on multisim. This time, instead of having something simple, you go, why don't you let this capacitor have some voltage or some charge on it? And what happens in time? So how does it come to steady state? Well, a lot of them don't even know what button to push on multisim. But again, setup, same units. Visualization now is more showing the transient effects die out, having a conversation to them about what are transient effects, what's the time period of transient effects. All of these become very, very important for the learning of the student. Now I tried to intersperse in things that were outside their experiences. Now for electrical engineers, I won't go through that, but I did more complicated visualizations. They know about electromagnetic fields, magnetic field. So I give them, here's a little line, so long, it's charged. What does the field look like? Okay, here's a magnet, it has a shape. What does the field look like? And if I have the field, can I rotate the thing around and do this? All of the things that you know how to do. And that was another learning tool. I brought stuff in for my own research. Says, you guys don't know this. You know nothing about game theory and finances and stuff like that. So why don't we do some game theory problems, okay? So we'll spend a day learning what is a game theory. We'll learn about matrices, min-max theorems, some neat ways to tie that stuff together, put it together, take a problem like the kids' rock, scissors, paper problem, try that. So that's kind of cool. And when you're all done, you can even make it time dependent and do some simulations. I just intersperse these things like throughout the quarter and just mention them, sort of like I am now. The purpose of my course, however, was I wanted to remember my outcomes to get them to think. So let me talk about the end game. What did we learn? How am I doing on time, by the way? Oh, I'm right on time, right? Okay. One of the successes was using Wolfram's textbook. I mean, not there aren't other textbooks out there potentially. The success was the textbook was so simple that they couldn't object. And yet it carried them through to very quickly get to advanced subjects. And they weren't embarrassed about it. I wasn't embarrassed about it. We just said, okay, this is what it does. And once they learned how to plot, they could do, gee, we did plot, now we're list plot, now we're doing plot. We did solve, now we're doing desolve. And I should say, when I would look at a group of students like electrical engineers, I'd say, you guys have to take, because I'm an A-bet accreditor, you guys have to take differential equations, right? Right. How many of you have taken a course on differential equations? Everybody's hand goes up. How many remember anything at all about them? Come on, somebody raise their hand. Can somebody even give me the name of a differential equation? How about y prime equals y? Is that okay? What? Couldn't think through that. But using solve and just introducing differential equations in Mathematica, say, I'm not going to ask you to differentiate it, integrate it, multiply it, divide it, anything. Just solve it and plot it. And tell me, if you vary this parameter, what happens, and start thinking about it, and what does this do? That they could do. So the textbook helped. I think the Mathematica was a really good tool to get them to think. Because I tried to challenge them with problems that were not in their discipline necessarily. And because there were 3 different disciplines, when I was talking to this group, these 2 groups didn't know that to start with. So we would do, for the software engineers, a graph theory problem, bring up a geomap like we're talking about in the last section. Here's a place in Europe, here's another place, find the shortest path between the 2. The software engineers would say, normally we would solve that with graph theory using Java. And they would come back in a couple of months and say, okay, we've solved it. Okay, a couple of weeks, but they wouldn't come back right away. Okay, this one gave them the ability to do it right away. The computer engineers and electrical engineers didn't know graph theory. They didn't know the nearest path stuff, and they didn't know the Bellman-Ford, and they didn't know any of that stuff. So they could get there also. Software engineers did not know simulations. But they learned simulations, and the electrical engineers would sit down and say, yeah, this is what you do, this is what you do, this is the equation. So they got it. So this was helpful. I did learn there is a value for engineers on the tools that they already have, and you can't replace that. One of the problems has been people try to go into schools like MSOE and say, get rid of MATLAB, Mathematica is better. No, look, their tools, Multisim, Java, they're not for thinking. They're engineering tools. They're simply cut and dry ways of getting the answer. And they're going to go into industry where those tools are used. They need to be proficient in those tools. There's nothing wrong with that. But I worked at a startup. I wouldn't hire them unless I could think they could think. So in addition to those tools, they need a Mathematica. They need a way to get out of that box and say, okay, you got a 1 farad capacitor with no special things, and you gave that to me as an answer? Come on. The student projects were the way I saw that. I saw them go into their discipline and go deep into what they knew, and I saw their thinking, like the L system. That was like out of the blue. I had asked them a question, draw for me a Sierpinski triangle, a Sierpinski dragon, okay, and and some fractals. And then they went away on a test, and they went away and they got that. So I would ask them, here's a flag. Give me the 3 closest flags to this Brazilian flag, okay? So pick this one, whatever it is. Now, I just give it to you. You don't know where it's from. Now tell me where that flag is from. Okay? That was on the final. And most of them got it. The final grades were actually pretty good. So I think Mathematica in the end was, my impression from talking to students is that, I'd ask them, was this of any good to you? Was this of help? Going to use this later in life? And they said, yeah, we're going to use this. This is really, they were kind of surprised. I had some students who, one of the things about teaching in different courses, in different disciplines, is I had many of these students in other courses. So, and I knew some of them were really pretty bright, and some of them were, not as quick. Doesn't mean they weren't bright, it just means like on a test, this guy finishes in half an hour, this guy finishes in 2. They both get to the end. Even with that kind of a spread, I got, everybody from that big spread, the very quick ones and the ones that were not so quick, enjoyed it. So basically, I was very happy. So I will take this opportunity to stop and thank you for your very polite attention and take any questions if I have time.